furan, pyrrole, and thiophene. At the end of the session, you should be able to write equations for furan, thiophene, and pyrrole when they undergo halogenation reactions. You should be able to compare the reactivity of furan, thiophene, and pyrrole using Federic acylation. You should be able to illustrate how furan, thiophene, and pyrrole undergo ring open reaction. So, in the halogenation reaction of thiophene, furan, and pyrrole, let's look at chlorination first. So chlorination of thiophene gives rise to two products. You have the 2-chloro-thiophene form and then the 2,5-dichloro-thiophene, right? So at this condition, negative 30 degrees Celsius, the two products are formed. So unfortunately, just one product is shown here, but pretty sure we know what 2-chloro-thiophene also looks like. But when N-bromo-succinimide is used, right, in the bromination reaction, then only the 2-bromothiophene is produced. So whenever thiophene reacts with N-bromosuccinimide in a bromination reaction, just one product is formed. The 2-bromo substituted form is formed. So next is to look at the iodination reaction. So in iodination of thiophene in the presence of mercuric oxide, here similarly the 2-iodothiophene product is formed. So what it means is in halogenation all the halogenation reactions of thiophene, it's only the chlorination that leads to the production of two products. That is the 2-chlorothiophene and then the 2,5-dichlorothiophene. But in bromination, just the 2-bromothiophene is formed. In iodination as well, the 2-iodothiophene product is formed. Now, this halogenated product can further be treated with other useful reagents to form a wide variety of important derivatives. So, the first step is to use your bromination to produce the derivatives of thiophene, and after getting these derivatives, other useful derivatives of thiophene as well can be synthesized using different chemical reagents. Now, the nitration of thiophene can also be done with concentrated sulfuric acid in an acetic anhydride, right? And in this reaction, only one product is formed. The 2-nitrothiophene is formed. So the nitro group attacks the carbon number 2 in the heterocyclic ring. Now, if the same reaction conditions are used in the case where there's an already substituted compound at the carbon number 2 position, then the incoming nitro group is forced to move to the fifth carbon position, right? So in this typical example, we have nitro being attached to the fifth carbon on the heterocyclic ring. So we have 2-methyl, 5-nitro, pyrrole. So this is typical reaction mechanism where the position number 2 is already occupied and then the incoming substituent is forced to attack the fifth carbon. Next is to look at the reactivity of thiophene, pyrrole, and furan in the Federic acylation reaction. Now, just as we said, now the reaction is usually carried out in different Lewis acid depending on the reactivity of the 5-membered ring. Now, just as we know, in order to compare thiophene and pyrrole's reactivity, you can make reference to the fact that reactivity is inversely proportional to stability, right? So it means that if a compound is more reactive, it means it's less stable, right? So if it's less stable, it wants to move into its stable state by reacting with other reagents or organic compounds compounds to make it more stable. So the trend in reactivity is that pyro is more reactive, because we talk about the fact that, because of the resonance structures we talked about in the previous session, thiophane's electron negativity is the least, right? So it makes it um, uh, have more stable resonance structures, which means that it will be less reactive, right? Now, because the electronegative atom in pyro is more electronegative than um, the nitrogen in furan and then sulfur in thiophane, it makes it have less stabilized resonance structures, making it more reactive than the other two um, heterocyclic groups, right? So the trending reactivity is pyro followed by furan and then finally thiophene. So the reactivity has a key role in the kind of Lewis acid that is being used in the Frederick-Kraft distillation. And because benzene is the least reactive among um, these groups, so if you have to consider benzene together with furan pyrrole and then thiophene, then benzene is the least reactive and therefore needs strong acidic medium to produce to undergo the Frederick-Kraft distillation, right? Now, and then because furan as well follows, furan also is slightly more reactive and therefore will require weak acid media to produce its um, Frederick-Kraft distillation product. So furan, which is more reactive than both thiophene and benzene, requires relatively weaker acid media, right? Now, the Frederick-Kraft distillation of pyro, because pyro happens to be the most reactive among the three, it requires very less reactive acid anhydride, even without the presence of a catalyst, to produce the acetylated product. Next is the sulfonation reaction of these heterocyclics. Now, what you need to take note is the reaction condition. So, concentrated H2SO4 can lead to the formation of the this is S, so thiophene, sulfonic acid. This is pyrosulfonic acid. But what you need to keep note of is the reaction condition involving the sulfonation reaction of thiophene and then of course pyro. Next is to look at the reduction in this reduction reaction of these three heterocyclics. Now the batch reduction, which involves sodium in liquid ammonia, produces the 2,3-dihydro product or the 2,5-dihydro thiophene product. So it's either producing this, that's the batch reaction, produces this, either one of these, right? And the catalytic reduction of thiophene usually results in N-butane. It's a complete ring open product of a four-membered hydrocarbon chain, right? An alkane chain. So in the catalytic reduction of thiophene, this product is never formed. The saturated heterocyclic ring is completely destroyed to form a straight chain hydrocarbon comprising 4 carbons. Now the next is to look at the reduction in pyro and furan. So realize that in pyro and furan, the saturated ring is obtained. So only the 2 double bonds are reduced to form a saturated heterocyclic ring, unlike in thiophene where the sulfur is detached from the heterocyclic ring to form an open straight chain hydrocarbon. That is completely different from what is seen in this slide. Next is to consider the ring opening reactions of these heterocyclics. So under mild conditions, furan can be hydrolyzed into the gamma dicarbonyl compounds. and with its reaction mechanism shown as well in acidic media. Now, pyro also polymerizes under the same condition, but thiophene is quite stable. So thiophene's um, ring opening mechanism is quite different from that which is observed between furan and pyro. Okay, so similarly, pyro also undergoes this same reaction mechanism, is the ring opening mechanism in the presence of hydroxylamine hydrochloride to give the dioxime form of butane diol. So this is the butane diol, the dioxime form of it. Now, desulfurization of thiophene derivatives occur with, yes, the Rani nickel catalyst that results in the sulfur-free saturated compound. So, in the ring opening reaction of thiophene, the derivative that is formed has no heteroatom in it, just like we saw in its reduction process. So the sulfur cleaves away and binds with the catalyst, leaving the straight chain resulting product without the sulfur. However, in the ring opening reaction of pyro, we realize that the nitrogen is still attached to a carbon in the open ring, and the same thing was also observed in the ring opening reaction of furan, right? So the exception is with thiophene in its reduction process, and then of course in its ring opening reaction process.